Namaste everyone. Welcome to second PUC physics class. We were discussing about magnetism and matter. Now we will go to the new chapter, that is electromagnetic induction. A small chapter again, similar to magnetism and matter. EMI. In short, we always call EMI, electromagnetic induction. A part of electromagnetic induction, you have studied it in your lower class, 10th standard. The discovery goes to Michael Faraday. He did some experiments, and a lot of thinkings were going on within the scientists about this electricity and magnetism. What is the source for electricity? What is the source for magnetism? And electric force and magnetic force, electrostatic force and magnetic force, and can't them be clubbed together? So this is one area where electricity and magnetism jointly take part in a phenomenon. And that's why the combination of electric and magnetic fields, the credit of that, one part of the credit goes to Faraday's experiment. What is Faraday's experiment? Faraday did one experiment. See, he took a coil like this. So he took a coil wound on a frame like this. So suppose this is the coil wound on a circular frame, and when you review it from one side, it appears like this. This is the other part of the coil like this. And when you take the two ends of the coil and connect it to a galvanometer, you know galvanometer contains another small coil around a magnet, and whenever current passes through it, it experiences a torque and it shows deflection. You can see it in the needle. And the galvanometer shows deflection only when the current passes through the coil. Okay, now there is no source for current here, isn't it? If there is, do you find any source of current here? No, not at all. And because simply galvanometer is connected to a coil, that's all. Now I will take a magnet and keep it here, like this, north and south. Now, if you keep this magnet very close to the coil and ask the coil, do you see anybody in your neighborhood? Yes sir, there is a magnet standing very close to me. And are you disturbed from the presence of magnet in the neighborhood? No sir, I am not disturbed, but the magnetic field of that magnet is passing through me, sir. That's all. The magnetic field due to this, see in the magnetic field lines, if you observe, they are coming like this, like this, like this, like this, like this. So the magnetic field lines produced by the magnet, of course, they go like this and they form closed loop. Magnetic field lines form closed loop. Electric field lines do not form closed loop. They never enter the conductor. Okay, so it is like this here. It is going into the south pole, right, and going out of the north pole like this. Okay, these magnetic field lines are entering into the coil. Coil says, sir, that magnet is stationary there and its magnetic field lines are passing through me. I am not disturbed now. The situation is a steady situation. Some magnetic field entering into the coil, and we call it as flux. Flux is the number of magnetic field lines passing normally through a particular area. Here, the coil area. And some of the magnetic field lines may be escaping like this. All the magnetic field lines may not be passing through the coil, some may be escaping, but a fixed amount of magnetic field lines are passing through the coil. So there is a flux linked with the coil. Flux linked with the coil. I can say it like this. There is a flux linked with the coil. Now, is there any change in the flux linked with the coil? Never. Because you ask the coil, how many magnetic lines of force are passing through you? Sir, some amount of magnetic field lines. And is there any change in it? No sir, the same amount of magnetic field lines. And I call it in the terms flux. You see, we defined electric flux. Remember, what do you mean by electric flux? Electric flux is the number of electric lines of force passing normally through the given surface. Similarly, luminous flux. What is luminous flux? The number of rays of light passing through the surface. As you go closer and closer to the source of light, that is bulb, the amount of rays of light passing through the bulb go on increasing. So that increases. Similarly here, if you bring this magnet closer and closer and closer, these two magnetic field lines which were escaping will also pass through this, if this coil is very close. As you bring the book very, very close to the bulb, the amount of light falling on the book goes on increasing, right? Suppose this is the bulb emitting light like this. Normal rays are coming out of the bulb. If you keep the book somewhere here, only two rays of light pass. Simply, I can't number the rays of light so easily. So you can see this, right? Only 2 rays of light pass through the book. If I keep the same book here, 3 rays of light pass. The amount of light falling on the book goes on increasing as you take it closer and closer to the source of light, because more and more rays will pass through or fall on the book. That is what you call flux. Now, magnetic flux is calculated like this. Better I explain what is magnetic flux and then go to this experiment. That is better, I think. So what is magnetic flux? Suppose there is a source of magnet and the magnetic field lines are moving like this. If you imagine a surface, of course now it is very easy to explain it because already you have seen what is electric flux. How many magnetic lines of force pass normally through this surface? Like this. Suppose the area of this surface is delta S, and this is the direction of magnetic field. You imagine a normal to the surface. Normal to the surface and magnetic field lines both are parallel, right? So flux through any surface, it is always measured in Weber. Unit of flux is Weber. Magnetic flux I am talking. The magnetic flux through any surface is the strength of the magnetic field and the area into cos theta. B delta S cos theta. Remember E delta S cos theta? That is, why cos theta, sir? It is to get the component. Suppose a surface is not normal to the magnetic lines of force like this. Magnetic lines of force are like this and the normal to the surface is like this. Then what you have to do? Take the component of this magnetic field along the normal, B cos theta. So then it becomes B cos theta or delta S cos theta. You can take the component of area along the magnetic field also. That is also okay. Because area here is a vector, it has a normal, right? Normal to the area is a vector. So if the magnetic lines of force are like this, take the component of the area in this direction. Or if the magnetic field lines are not along the normal, take the magnetic field lines along the normal, that component. So when you get the component of this here, it becomes B cos theta. So B cos theta into area gives the magnetic flux. You can express magnetic flux in 2 units. One is Weber, another is Tesla meter square, because magnetic induction is flux per unit area. Flux of magnetic field per unit area is called magnetic induction. Yeah, right. Flux per unit area. Then what is flux? Magnetic field into area gives the flux. This flux is Weber, W-E-B-E-R, Weber, or Tesla meter square. That is also possible. Tesla meter square or Weber is the unit of magnetic flux, and it is given by B delta S cos theta. Now these magnetic lines of force, I will come back here, right? I need not have to spend more time in this flux because you have already studied electric flux. Just you have to remind it, that's all. Now coil says, I am not disturbed by the magnet because it is passing some magnetic field lines through me. Let them pass, but they are not changing with time. So what reading is shown by the galvanometer? 0. You ask galvanometer, why are you not showing any current? Because sir, no current is passing through me. There is no battery, nothing. No current is through the coil. So how should I show the current? No current. Okay. Everything is agreed. Now take the magnet forward. Just take the magnet forward. When you take the magnet forward and backward like this, you will find that there is a current in the galvanometer. This experiment was done by Michael Faraday. Michael Faraday said that when you take a coil towards the magnet and take it away from the magnet, you get a deflection in the galvanometer. And the deflection in the galvanometer remains only as long as the magnet is moving. If the magnet is stationary, the deflection becomes 0. Why it is so? So he concluded finally, an electric current is induced in this coil, or an electric current is produced in the coil only when the magnetic flux linked with the coil keeps on changing. You see how the two entire different things are clubbed. Electric current is an effect due to electric field, right? Because flow of charges need electric field, and magnetic field here, they are clubbed together. Change in the magnetic flux can induce a current. that can produce a current. So they have some relationship. So whenever a coil, closed coil connected to a galvanometer is kept very close to a magnet, and if the magnet is moved towards the coil and away from the coil, we get a deflection in the galvanometer, indicating that there is a current in the circuit, closed circuit or coil, and that current is called induced current. We name it as induced current because this is induced due to some change, right? Induced current or induced EMF. Of course, you should get an EMF also here. Without EMF, you won't get a current. So there is an induced EMF in the coil. This phenomenon is called electromagnetic induction. You see, both are related, right? So what do you mean by electromagnetic induction? The change in the magnetic flux linked with a coil induces a current in the coil, and this phenomenon is called electromagnetic induction. Change in the magnetic flux linked with any closed coil induces a current in the coil, or production of current in a coil through which the magnetic flux is changing is called electromagnetic induction, and the current produced is called induced current, and the EMF generated is called induced EMF. Okay, the experiment doesn't get ended here. He just continued this. When the magnet is moved forward with certain speed, he finds that there is a deflection in one side, showing that there is a current flowing through the coil in one direction. Say like this. When the magnet is taken away with the same speed, it is found that the deflection of the galvanometer is in the opposite direction and showing the current in the coil in the reverse direction. So when the magnet is taken towards the coil, a current flows through the galvanometer in one direction, and when the magnet is taken away from the coil, current flows through the coil in the another direction. So induced current direction keeps on changing when the magnet is moved towards the coil and away from the coil. That means when the flux through the coil increases, moving the magnet towards, flux through the coil increases, current in the coil is, induced current is in one direction. When the flux through the coil decreases when you take it away, as if you are taking a torch away, amount of light will be less here. Similarly, when you take the magnet away, the magnetic field lines passing through this surface will be lesser and lesser. So when you take the magnet away, the current will be in opposite direction. Induced current flows in the opposite direction, deflection is in the opposite direction. That is one part. So induced current flows in one direction when flux increases, and induced current flows in another opposite direction when flux decreases. And no induced current is seen when the magnet is taken or magnet is kept stationary. That means flux is constant. Remember, when the magnet is kept stationary, don't be under the impression that there is no flux. There is flux. There is a flux linked with the coil, but it is not changing with time. It is constant. It is constant with time. So change in flux only induces a current. That is the best conclusion, right? A current is induced in a coil only when there is a change in the magnetic flux. Doesn't mean that current is induced in a coil when there is a flux linked to the coil. There is a flux when the magnet is stationary, but it is not changing, no current. So if at all you need an induced current in a coil, you need the magnetic flux through the coil changing. That is a very much needed fact here. There should be a change in the magnetic flux. Change is very important. So you produce the change either by moving the magnet towards the coil or away from the coil. One more conclusion from Michael Faraday. If you take the magnet very fast towards the coil, deflection is more, indicating that more current flows through the coil. And if you take the magnet away from the coil, deflection is more but in the opposite direction, indicating that more induced current is flowing in the opposite direction. So all these experimental phenomena are given by the Michael Faraday, and he says whenever the magnet is moved towards the coil, there is a deflection in one direction. When the magnet is taken away, there is a deflection in the opposite direction. When the magnet is taken faster towards the coil or away from the coil, the induced current was more and more in the forward and reverse directions, and the deflection of the galvanometer will be more, indicating that there is a more current. And all these things made him to conclude that an induced current flows in a closed coil only when there is a change in the magnetic flux, and this induced EMF lasts or remains in a coil only as long as there is a change in the magnetic flux. This induced current flows only as long as there is a change in the magnetic flux. So rate of change of magnetic rate of change of magnetic flux linked with the coil is directly proportional to the induced EMF generated across the coil. Without this EMF, no current can flow, so there should be an EMF also. So induced EMF in a coil is directly proportional to rate of change of magnetic flux, or you can write it as induced EMF is equal to minus d phi by dt. There is no constant of proportionality, it is 1. Why minus? That we will see later. So induced EMF through any coil is equal to rate of change of magnetic flux. This is Faraday's law. Right? Faster you do change, more will be the induced EMF. Slower the change, lesser. If phi is a constant, what do you mean by phi constant? Differentiation of a constant is 0. What do you mean by phi constant? When you take the magnet, or when you keep the magnet here only, stationary, there is a flux linked with the coil. Don't be under the impression that there is no flux. There is, but it is not changing with the time. Phi is a constant, then differentiation of a constant is 0. No, that means there is no change, that's all. So induced EMF is 0. So induced EMF in the coil flow, or induced EMF is developed only as long as there is a change in the magnetic flux. Okay, that is the first experiment done by Michael Faraday. You may be asked for the exam, what is electromagnetic induction and what is the first law, or what is the Faraday's law? The rate of change of magnetic flux is directly or is equal to the induced EMF in the coil. Okay, well, minus sign we will discuss it later. Okay. Right, one thing. Now, in what ways you can produce the flux here? A change in the flux or induced EMF? There are many things. Either keep the magnet stationary, or take the coil and all these things away and towards the magnet. That is also possible. You need not keep on dancing with the magnet. Suppose the magnet gets tired, magnet says, how many times I have to move forward and backward? I will keep stationary. Now let the coil move backward and forward, so that the galvanometer shows deflection, because that also produces the change in the flux. Either you have to bring the torch towards the book or away from the book if you want to get different intensity of light on the book, or keep the torch stationary. If your right hand is tired, take the book in the left hand like this. So either magnet should move towards the coil or away from the coil, or coil should move towards the magnet and away from the magnet. If you move both like this with the same speed, no use. If you move both torch and book with the same speed, no change in the flux or change in the luminous flux or light on the book. So if you move the magnet and coil both with equal speeds in the same direction, no use. But with equal speeds in the opposite direction is useful. How? You take the magnet and coil away like this, so it produces double EMF. I can remember one of the entrance exam question. Induced EMF in a coil, when the magnet is moved towards the coil, is E. What is the induced EMF? If both are moved towards each other with the same speed, double E, because relative velocity is 2V, right? So if only magnet is moved towards the coil, it is E. If both magnet and coil are moved towards each other, it is 2E. Away from each other, 2E. Same, but minus 2E, that's all. Same direction? No, 0. Because there is no change in the flux. If magnet and coil are moved in the same direction with the same speed V, what is the induced EMF? 0. Because there is no relative motion. Of course, you can move the coil also here and there. Why can't you rotate the magnet with this as axis? You take this as axis, rotate it like this. I will take the duster and I will show you. Duster has gone away. Yeah, you rotate it like this. Why can't you do it like this? That's also possible. Once north pole comes, another time south pole comes. When it is like this, the magnetic flux linked with the coil will be 0, because coil is like this. All the magnetic field lines are like this. So when it is like this, maximum magnetic field passing. So if you hold the book like this and put the torch like this, what is the use? Torchlight is coming like this, it is not falling on the book. So either you can move the torch, rotate the torch, or move the book like this. Anyway, so if you can rotate the magnet, turn the magnet, either like this or like this. That's also possible. So you see how many. So now the most needed factor is change in the magnetic flux. That you know. So change in the magnetic flux linked with the coil induces an EMF in the coil. That is electromagnetic induction. How do you produce the change? How do you bring the change? Either move the magnet, move the coil, rotate the magnet. That is also possible. Rotate the coil. That is also possible. Keep the torch, rotate the book. When the book is like this, maximum light falls on the book. When the torch and books are like this, maximum light falls on the book. Turn it, minimum light. Maximum, minimum, maximum, minimum. So you can turn the coil. Now flux linked with any coil is given by that formula just I have discussed, right? Okay, we will go to the things later. We will see how to produce the change first. Flux linked with any coil or any surface. Where should I? Suppose this is the surface and its normal is like this. If the magnetic field lines are crossing like this, B, and normal is like this, if this is theta, okay, then if the area of this is A, I don't take it as delta, as full area A, then what is the flux? Magnetic flux of magnetic field, B, A cos theta. Either you take the component of A, this is normal area vector like this, or take the component of B along the direction. So if you want to have any change in phi, bring changes in any one of these, enough, isn't it? Bring the change in either magnetic field or area or cos theta. Anything is possible. So what is cos theta change, sir? Just change the direction of this area. That is what I told. When the coil is like this, see, this is the coil, right? Magnetic coil. And when normal to the coil is like this, and magnetic field lines are passing like this, theta is 0, right? Cos 0, 1 or 180. Cos 180 is -1, highest value. When the coil is like this, magnetic field lines are passing like this. They are not passing through the coil. They are simply passing, grazing the coil like this, right? No use. Theta is 90, magnetic field and area normal. Cos 90 0, no flux. So just change it like this. When you change the area of the coil or normal to the coil, keep on rotating it, you are changing cos theta. That is also possible. Now change the magnetic field strength. Take the coil away, magnet away, that is B, changing B. What is changing? Area. Only area. That is very important. You can change the size of the area. Sir, can you change the size of a coil like this? Suppose there is a magnet here and here is a coil. Remember, you change the area of the coil. Area less, area more. Area less, difficult, isn't it? But you have an arrangement how to do that. We will see that later. So change in the magnetic flux can be brought about by changing the magnetic field, taking the magnet away, towards, changing the orientation, cos theta, changing the area, anyway, and changing the number of turns also, because magnetic field produced by any coil or so, it depends on number of turns also. See, these magnetic field lines are passing through this coil, right? How many turns in the coil? Every turn is enjoying the magnetic field lines, right? So number of magnetic field lines. Can't you change the number of turns? That's also possible. You can change the number of, sir, how can we change the number of turns all of a sudden? It is possible. Let us see how it is so. So change in the magnetic field linked with the coil can be brought by changing the strength of the magnetic field, changing the area of the coil, angle cos theta, and number of turns. These things you have to remember. NBA cos theta. This formula is very, very important. Till the next coming chapter also, they end up. This NAB cos theta is very, very important. So flux linked with any coil is given by NAB cos theta, where N is the number of turns, A is the area of the coil, B is the strength of the magnetic field, and theta is the angle between the magnetic field and the normal to the area. That is also very important. Angle between normal to the coil and the magnetic field. Yes. Okay. So this experiment may be asked. Describe coil and magnet experiment done by Michael Faraday to explain electromagnetic induction. You can select it, but give the last preference for this question, because if it is asked for 3 marks, say, you have to give 1 mark for diagram. 1 mark for diagram means you have to draw a very huge diagram for 1 mark, and if something goes wrong, 1 mark is gone. You will take a lot of effort, or you put a lot of effort to draw that 1 mark diagram, but if something is missing in that, you will lose all the 1 mark, right? So better not to choose, and you have to write all the stories that this is brought here, and better you select some 3 points writing questions, like write 3 properties of magnetic field lines. That is better. So if you get such questions, give first preference to that, and next preference to this Faraday's experiment. I didn't say that you shouldn't study this, okay? Don't turn that teacher has asked me and he has told me that don't study first experiment done by Michael Faraday. No, you have to study it. But select that question if there is no other option. That is what I am saying, right? Don't turn my sentences. You can select this question, or if you don't know anything else in that 3 marks options. Suppose you know other things, better you select, because it is a very a lengthy answer. Michael Faraday did one more experiment, that is coil and coil experiment. You had coil and magnet now, coil and coil. Sir, what about magnet? That magnetic field is produced by another coil itself. That is better, right? You take a coil, okay, this is the coil, and its other part is visible like this, and this contains a galvanometer as earlier, right? And okay, and here is another coil, and its other part is here with a battery and a key like this. Coil and coil, coil 1, coil 2. I can call this as primary coil and secondary coil. That is also possible. This is galvanometer. Instead of another magnet, I took a coil, that's all. Because you know that any current carrying coil produces a magnetic field, right? Any current carrying coil produces a magnetic field. So you need not worry about you need not worry to take a magnet itself. Take another coil, and this produces magnetic field along its axis, and that passes through this coil also. Okay, so this is the axis. Okay, let there be coaxial coils. The magnetic field produced by this coil passes through this coil. Magnetic field lines, I call. So it is like this. It is like this. Some of the magnetic field lines may escape away, but some of them pass through the other coil. This is coil 2 and coil 1. I can call it as primary and secondary coil also. Now, of course, this diagram is wrong because I have not switched it on. Still, I am showing magnetic lines of force, right? Okay, I will switch it on. And okay, here it should be coming in, right? If it is going out here, it should be coming in. Going out, and here coming in like this. Okay. Now, suppose you have 2 coils. One coil connected to a battery with a switch. Another coil placed in the neighborhood of coil, first coil, that is the primary. Secondary is placed very close to it. It should be very close because the magnetic field lines should be passing through this coil. You shouldn't keep this somewhere away and say that no induced current flows. So this should be with the galvanometer. Now, as soon as you switch on this coil, you get a momentary deflection. Why? As soon as you switch this on, what happens is a current passes through the primary coil. That current produces a magnetic field, and you know that any current carrying coil produces a magnetic field. What is the formula for the magnetic field produced by a current carrying coil? Along the axis here at a distance x from this coil, because this is the coil which is carrying current. B is equal to mu naught I r square, of course, yeah, number of turns, divided by 2 into r square plus x square to the power 3 by 2. That is the magnetic field produced by this coil here. But remember, this is current I, which is a steady current, DC current. Won't it produce a fixed magnetic field? Or won't it produce the fixed magnetic lines of force passing through this coil? Does it produce any change in the magnetic flux? Faraday says induced EMF will be developed only when there is a change in the magnetic flux. d phi by dt, phi should change with the time, minus sign, which we are going to discuss later, minus sign. D phi, induced EMF is minus d phi by dt. But is it changing now? Because we have a steady current here. Battery is a DC battery. Yes, because whatever be the DC battery it is, when a DC battery is switched on, all of a sudden current doesn't increase to maximum. Suppose it is a 5 ampere battery, say. I have a 5 ampere battery. I'll connect it to a circuit. Okay, I'll connect it to a resistor and I measure the current. As soon as this is switched on, current doesn't increase to highest value all of a sudden. Current increases steadily and then reaches the maximum value. It takes certain time to increase, maybe fraction of second, microseconds, milliseconds. It doesn't take hours and hours. If it is so, if you want to do experiment today, then you should have switched on the circuit 1 hour earlier, right? Before suppose next hour is the practical hour, you should go now, switch on, construct the circuit, switch it on and come to the language class or some other class and then go to the laboratory. By that time the current will be maximum. But it is not so. It takes a very, very less time, fraction of a second, even maybe microseconds, to reach from 0 to the maximum value. Say this is 0, this is I in ampere, say this is time. Okay? It reaches the maximum. Now, what about the type of magnetic field produced by this coil during this journey, starting from 0 and reaching the maximum value? It is varying magnetic field, because suppose the current is 5 ampere, initially the current passing to this coil is 0, then 1 ampere, 2 ampere, 3 ampere, 4 ampere, 5 ampere. What about the magnetic field produced by this coil? Growing, growing, growing. What about the magnetic field here? It is also growing till it reaches 5 amperes. So there is a change in the magnetic flux. Once it reaches maximum, it is steady. There is no decrease. There is no increase. It is a constant. When constant current is passed through the coil, does it produce any magnetic field? Yes, it produces a magnetic field according to the current, but it is not changing with time. No EMF. So EMF is induced in this coil. If you connect a voltmeter here, you will get an induced EMF. And you can see a current flowing through this galvanometer. Galvanometer shows deflection. There is an induced EMF, there is an induced current. And induced current and induced EMF is obtained, and galvanometer shows a momentary deflection when you just switch it on. Suppose it is switched on permanently, then the deflection becomes 0, because current reaches the steady value. Once the current reaches the steady value, magnetic field produced by the primary coil, of course I can't say there is no magnetic field, there is magnetic field. Magnetic field produced by the primary coil is a steady value, a steady magnetic field, it doesn't change with time. So induced EMF minus d phi b by dt, I have written this formula somewhere, it is here. It is a constant one, it becomes 0. So when a coil is kept very close to another coil connected to the galvanometer and a current is passed through the primary coil, a momentary deflection is observed in the galvanometer when the primary coil is switched on. Battery of the primary coil is switched on. And then the deflection disappears. When it is switched off, again a momentary deflection is observed in the secondary coil, but in the reverse direction. Why? Because once the 5 ampere current is passing through the coil steadily, when you switch it off here, current should reduce from 5 to 0. It doesn't reduce to 0 all of a sudden. It takes certain time to decrease from 5 ampere to 0 ampere. 5, 4.5, 4, 3, 2, 1 like this. And during that time, the magnetic field will be collapsing here. So magnetic field linked with the coil will be collapsing. That induces an EMF in the reverse direction, and induced current in the reverse direction. Galvanometer shows deflection in the opposite direction, and again you get a current. And once the current becomes 0, like this, then no deflection in the secondary coil, because there is no change in the current, right? So I'll rub this in order to show the graph properly. These are the magnetic field lines. So now this is time. Now here is an interesting thing. So if you want to get a continuous deflection in this galvanometer, what you have to do then here? I want the continuous deflection. Either the galvanometer must show the deflection in this direction, or this, or this, or this. There should be a continuous deflection in the galvanometer. What should I do for that? I should keep on switching this on and off, on and off, on and off. If I keep it switched on permanently, once I will get the deflection. Once the current becomes steady magnetic field, and no change means induced EMF becomes 0. So one deflection, again 0. Switch it off, magnetic field, let it collapse, because current collapses here, magnetic field collapses here. As the magnetic field falls, again deflection in the opposite direction. Once the magnetic field becomes 0, because current becomes 0, deflection is 0. Because there is no change again. There is no magnetic field itself. There is no change also. So again switch it on, switch it off. Now if you keep on doing like this, then you will get a lively current here. In one direction, another. But you can't do this every now and then here. So you can do one thing. You can connect an AC here, AC battery. What is AC? AC changes its value every now and then by itself, isn't it? AC changes the value by itself. You need not switch it on and switch it off every now and then. AC increases, goes to the maximum value, decreases, becomes 0, minus maximum 0, like this. It keeps on doing it like this. So then you will get a permanent deflection here, right? So you will get a current either flowing in one direction or induced current flowing in the opposite direction. Any one direction you will get. Now, of course, you can do another thing as you did in the last experiment, that is Faraday's first experiment. You can keep it on, switch it on, keep it switched on, and now it is a magnet, right? Because a coil produces a magnetic field. Take this coil towards this coil and away from. That is the first experiment itself. Or you can switch on and switch off. Now here is an interesting question. Current in this battery, when the battery is switched on, increases from 0 to maximum. There is an increase in the magnetic flux. There is an induced EMF. There is an induced current. Okay, one deflection. Switch it off. There is a collapse of current. And current collapses taking certain time to become 0. Magnetic field decreases. So magnetic field collapses. There is an induced EMF, but in the opposite direction. Induced current, reverse direction. My question is, what is the amount of induced EMF and induced current? Magnitude wise, they may be in opposite direction. Once the current may flow like this in the coil, another time reverse here, induced current. What about their magnitude? What is the magnitude of induced EMF developed during the circuit switched on? I will call it as make. Make means switching on the circuit. What is the induced EMF? Amount of induced EMF, magnitude of induced EMF during make. And during break, break means switch it off. Are they equal? The induced EMF developed in the coil when the coil, the primary coil current is switched on and switched off. During make and break, when you switch on and switch off, induced EMF developed in the secondary coil are of same value or different value. They are of different values because the change in the flux when the current grows here and the change in the flux when the current falls here are not the same. Not the same means with respect to time. When you grow, when you switch it on, when the current grows, I will come back to this graph. When the current grows from 0 to maximum, it takes a longer time to grow from 0 to maximum. When you switch it off, when the current falls from maximum to 0, it takes a lesser time to fall from maximum to 0. So this is during make and time during make, and this is time during break. Right? So current takes longer time to grow but very short time to fall. That means where the rate of change of flux is faster or more. The change in the flux is faster, where does it take lesser time? That is during break. During break, current collapses from maximum to 0 all of a sudden compared to during break. So EMF developed during break, that is when you switch it off, is more than the EMF developed during break when you switch it on. Hope you have followed. Taking lesser time means activity is going on very fast. Taking more time means activity going on very slowly. Make is a very slow process. Break is a very fast process. So rate of change is faster during break, more induced EMF. Rate of change of flux is slower during make, less EMF. So during make, EMF induced is less. During break, EMF induced is more. One more thing. The EMF induced during make is called back EMF. Sir, reverse names you see. Back EMF. And this is forward EMF. Okay? Forward EMF and back EMF. Now, so why do you call it as reverse name, sir? During make, you should have called it as forward EMF, and here it has back EMF, because induced EMF is opposite. Opposite to what? That we will see later, right? E is equal to minus d phi b by dt, rate of change of magnetic flux. Now, when you switch on a primary coil, EMF induced in the secondary coil is called back EMF. When you switch off a primary coil, magnetic field collapses and the EMF induced in the secondary coil is called forward EMF. Which is greater among them? Forward EMF is greater than back EMF because collapse is faster. Forward EMF is greater than back EMF. Of course, you don't have this information in the NCERT syllabus, but it is easy to understand, right? So this is coil and coil experiment. Faraday did very important two experiment, coil and magnet experiment, coil and coil experiment, which proved that any change in the magnetic flux linked with any coil closed circuit induces an EMF in the closed circuit, and that induced EMF is equal to the rate of change of magnetic flux through the coil. Of course, E is equal to minus d phi by dt. This is Faraday's law, and he proved it using two experiments wherein he tried to change the magnetic flux linked with a coil using a magnet and another coil, and he was able to produce induced current and induced EMF. Okay, so change in the magnetic flux can be made using many ways. BA cos theta, you know this one. You can change the angle between the two coils. Here also you see, you can change the angle between these two coils, right? Keep this coil stationary, rotate this coil. When you rotate this coil, maximum flux passes through this like this, because now normal is making an angle 0 with the magnetic field lines, cos 0, 1, highest. Now, theta 90, cos 90, 0. So you can turn this coil, you can bring them closer and away, and you can make many circles here, right? You can change the magnetic field in many ways. So you can change the area of this coil. You make this coil smaller, larger. When it is smaller, only few magnetic lines of force, and larger, many magnetic lines of force. So you can change the area, theta, everything. So that these are the two experiments, very important experiment. So we have covered what is electromagnetic induction, what is Faraday's law, explanation of first and second experiments done by Michael Faraday to demonstrate electromagnetic induction, and in the secondary experiment, that forward EMF, back EMF, and making a circuit, breaking a circuit. So whatever it is, finally you need change in the magnetic flux, that's all. So magnetic flux must keep on changing linked with the coil, then only it induces an EMF. Of course, if there is a flux which is constant, it doesn't induce any EMF at all. So that is the important beginning of this electromagnetic induction. Then we will see in the next class why does the negative sign appears here, and that is in accordance with another law called Lenz's law, which is also very important. And let us try to change the area of the coil, how to change the area of the coil, and an induced EMF in a rod moving, which is a very important derivation, rod moving in a magnetic field, and some very simple things in this chapter. There is no big derivation here, right, except the self-inductance of a coil. That is a little bit complicated derivation, but if you understand it, it is very simple, and then we will see. But very important chapters, please don't miss these things. Try to study them so that it becomes very easy during the time of examination, because these chapters will be always dealt during the time of examination. So if you know everything already, you can be very cool in the class and you can listen to all these things. So thanks for watching the class. Hope you have enjoyed the class, right? And there is not much involved in this once you understand it. So let us meet in the next class with lot of things like Lenz's law, and we will continue, right? Hope you take care of your health and don't waste the time. Thank you.